Hello and welcome. Today, we're becoming material detectives. We're going to crack the code on a really basic but huge question. What is all this stuff around us actually made of, and why does it act the way it does? So check this out, a solar park. It's got silicon, glass, and metal, all working together. One is shiny and carries electricity. Another you can see right through. And the third is this weird thing called a semiconductor. They're all solid, right? But they behave so differently. So why? Well, the answer isn't on the surface. It's deep down at the atomic level, in how they're built and bonded together. So here's our game plan for today. First, we'll cover the absolute basics. What makes something pure, mixed, or combined? Then, we'll investigate the two big categories of materials, the super strong giants and the much weaker molecules. And finally, you're going to put it all together and become the detective to solve a little chemical mystery yourself. All right, section 1. Let's start with the absolute fundamentals. Okay, let's break it down. An element, super simple. It's just one type of atom, and that's it. A compound is where things get interesting. You have different atoms, but they're chemically locked together in a very specific ratio. You know, like H2O. It's always 2 hydrogens for every 1 oxygen, always. And a mixture? Well, that's just a bunch of stuff thrown together without any chemical bonds, kind of like tossing salt and pepper in a bowl. Now, here's a huge detective clue for you, the melting point. Elements and compounds have a sharp, fixed melting point. Mixtures, though, they get all mushy and melt over a range of temperatures. Remember that one. Let's zoom way in and see what this looks like. See the elements? All the little circles are the same. Now look at the compounds. Notice how the different colored circles are stuck together in a neat, repeating pattern? They're bonded. And then there's the mixture. It's just a total free-for-all. Different things are all in the same space, but they're not really interacting. Getting this difference down is your first big step. Okay, on to section 2. Now we're talking about the giants, materials that are basically built like atomic fortresses. We're going to look at 3 types of these giants. You've got your ionic lattices, like table salt, then giant covalent structures, like a diamond, and finally, giant metallic lattices, like the copper and wires. The one thing you got to know about all of them? They have crazy strong bonds holding them together in all directions. So this explains something kind of weird. Why is salt, which is pretty hard, also so brittle? Well, look at the left. It's a perfect, orderly grid. Positive ions next to negative ions, all attracting each other. It's strong, but watch what happens if you hit it with a hammer. See, on the right, the layers slide just a little bit. But now, positive is next to positive, and negative is next to negative. They repel each other with a huge amount of force, and snap, the whole thing just shatters. And here's another key clue about these ionic compounds. Electricity. When it's a solid, like you see here, those ions are totally locked in place. They can't move, so electricity can't flow. But if you melt it or dissolve it in water, suddenly those ions are free to zoom around. And since they're charged, they can carry an electrical current. So if you find a substance that only conducts electricity when it's melted or dissolved, ding, 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 you've almost certainly gotten an ionic compound. This is one of my all-time favorite examples. Look at this. Both a diamond and the graphite in your pencil are made of exactly the same thing, pure carbon atoms. That's it. So why is one the hardest thing we know, while the other is so soft it literally rubs off onto paper? It's all about the structure. A diamond is a perfect 3D fortress of strong bonds in every direction. But graphite, it has strong bonds too, but only in flat sheets. And between those sheets, the forces are super weak, so the layers just slide right off. See? Structure is everything. All right, what about metals? How are they so strong, but you can also bend them into different shapes? The key is this amazing idea you see here, a sea of delocalized electrons. Just picture it. You've got this grid of positive metal ions, and all of their outer electrons have just detached, and they're flowing around freely between all the ions, like a sea. This sea of electrons acts like a super strong but flexible glue holding the whole thing together. And here's why that electron glue is so brilliant. When you push on a metal, like when you bend a paperclip, the layers of ions can slide past each other pretty easily. But because that sea of electrons just flows right along with them, the metallic bonds never actually break. It's incredible. Think back to that salt crystal. It shattered because its bonds were rigid. The metal bends because its bonds are flexible. It's a total game changer. All right, section 3. We've talked about the big, strong giants. Now let's look at their opposites, the small, weak molecules. These guys are the reason we have so many liquids and gases. Okay, this is probably the most important distinction of the day. For these simple molecules, the issue isn't the bonds inside the molecule. Those covalent bonds are still really strong. The key, and I mean the key, is the weak forces of attraction between one molecule and its neighbor. Because those forces are so weak, it takes barely any energy to pull the molecules apart from each other. And that's why they have such low melting and boiling points. Take a look at liquid bromine here. The bond holding the 2 bromine atoms together inside that little molecule, that's a strong covalent bond. But the force pulling that molecule towards the molecule next to it, that's super, super weak. So when you heat it up and it boils, you are not breaking the strong bond inside the molecule. You're just easily overcoming those weak forces between the molecules, letting them fly off as a gas. Understanding that difference is absolutely critical. Section 4. Okay, you've got the theory. Now it's time to put on that detective hat and actually use this knowledge. So imagine this. I hand you a little vial. Inside is a white solid. Solid X. That's all you know. How do you figure out what it is? What tests would you run? What questions would you ask? Remember, the properties of the substance, how it behaves, are your only clues. Now, every good detective needs a plan, a guide. And this flowchart, this is your guide. It's a thinking tool. It lets you take simple observations like, does it melt? Or does it conduct electricity? And follow a path of logic to figure out the deep down structure of whatever you're looking at. Okay, here we go. Your first case, you have solid A. Clue number 1. As a solid, it does not conduct electricity. It's an insulator. Clue number 2. When you dissolve it in water, it does conduct electricity. Okay, take a second. Think about what we've talked about. What's your deduction, detective? So, did you crack the case? Let's trace it on our flowchart. We start at the top. Does it conduct electricity when molten or aqueous? Yes, the clue says it does, so we go down that path. Next question, does it conduct electricity as a solid? No, the clue says it's an insulator. We follow that path, and it leads us to only one possible conclusion. It has a giant ionic structure. See? The properties tell you the story every time. So really, the biggest takeaway from all this is pretty simple, but it's also profound. The invisible, tiny, atomic-level world, the world of structure and bonding, is what determines everything about the big, visible world that we see and build things with every single day. And this knowledge points directly to the future. What you're looking at here are graphene, a single sheet of carbon atoms, and a carbon nanotube, which is just a sheet of graphene rolled up. These are real materials with properties that sound like science fiction, all because of how their carbon atoms are arranged. So, I'll leave you with a final detective question. Based on everything you've just learned about structure and properties, what kind of amazing things would you build with these materials? Think about it. Thanks for joining me.